Now we're going to learn about Newton's second law of motion. Remember, with Newton's first law, an object at rest is going to remain at rest, or an object that is moving at a constant velocity will continue to move at a constant velocity unless an unbalanced force is applied to the object. Well, Newton's second law deals with what happens when we have an unbalanced force applied to our object. So if we do have that unbalanced force, the object is going to accelerate or change its motion in the direction of the unbalanced force. So for example, in this picture, if the ball is kicked and the force is applied to the right, then the acceleration or change in motion will also be to the right. Here we have the ball that was already moving to the right, but now the net is applying a force to the left, and that means that our acceleration will be to the left. This will be slowing it down. Now, a couple of important statements that you need to understand about Newton's second law. When we have an unbalanced force, it will always cause an acceleration. So an unbalanced force and an acceleration always go together. The opposite then is also true. If there is an acceleration, a change in motion, there must be an unbalanced force that caused it. You cannot have an acceleration if there was no unbalanced force. And the other thing you have to know is that acceleration is always in the same direction as the net force. They always have to be in the same direction. Now, Newton's second law gives us an exact relationship between force, mass, and acceleration, and is expressed mathematically by both of these formulas. This formula is the one that's going to be on your AP Physics formula chart. But you often hear Newton's second law described as F equals ma. But you have to be careful with this because it's not just any force is equal to mass times acceleration. It's the net force, or the sum of all of the forces, is going to cause an acceleration. It's not just a single one, it's the sum of all of them. Now, what we know from this is that from the equation, we can tell that acceleration is directly proportional to the net force. So we can see that by this part of the equation. Acceleration and net force are on opposite sides of the equal sign, and they are both in the numerator. So they are going to be directly proportional. That means if I increase my net force, my acceleration will also increase. Or if I decrease my net force, my acceleration will also decrease. So if I double my force, if I push twice as hard on something, then I can expect to have an acceleration that's twice as great. They will be directly proportional. Now we can also tell that acceleration and mass are inversely proportional. Acceleration is proportional to 1 over the mass because mass is in the denominator. So if I increase the mass of my object and I push with the same force, then my acceleration is going to be smaller. So if I push my object with the same force, but it has twice the mass, it will only accelerate half as much. So if I have my masses doubled, then my acceleration is only going to be 1/2 what it originally was. So let's try a couple of questions. Given the net forces and the masses on the blocks shown, we need to know which two blocks have the same acceleration. So remember, acceleration is equal to the net force over mass. So my force divided by mass is going to give me my acceleration. My force divided by mass will give me acceleration. Force divided by mass, and then force divided by mass. So your answer should have been A and D. So this is the same question, well, similar question to the one we did in the Newton's first law video. Now, you probably remember that A and B both had balanced forces. So we had 2 up, 2 down, 4 up, 2 and 2 down, or 4 down. So these were balanced. So there's no acceleration when the forces are balanced. Here we have 2 up, 2 and 4 down. So 2 up, 6 down. So our net force is going to have a magnitude of 4 in the downward direction. Now, I don't know what each of these blocks means, but I just know that this is going to be my ratio. Again, 2 up, 2 and 4 down, so 6 down. So again, we're going to have a net force with a magnitude of 4 in the downward direction. So C and D would have been the correct answers here. Now, as we go through problems with Newton's second law, they are going to get more complicated, but just so you know right now, when we're solving these problems, you may need to find acceleration in several different ways. One of those is you may have to use a graph. So for example, here we have a velocity time graph, and you could get a question like this. A block experiences varying net forces over time. If the mass of the block is 5 kilograms, what is the magnitude and direction of the net force at the 3 time periods in the graph? So here we have, we'll say this one's A, B, and C. Now for acceleration, remember, acceleration is the slope of a velocity time graph. So if I need to know what my net force is, I know what my mass is, then I need to know what acceleration is. Because remember, acceleration is the net force divided by the mass. So my net force is equal to my mass times acceleration. So I know the mass, it's not changing, it's 5 kilograms. So now I need to know what my acceleration is. So to find acceleration, remember it's the slope. So in this one, we go up 3 and over 2. So my slope or acceleration is 3 divided by 2, or 1.5 meters per second squared. So my force in segment A is my 5 kilograms times my acceleration of 1.5 meters per second squared. And so that's going to be 7.5 newtons in the positive direction. Now B has a slope of 0. Its velocity is constant. Well, remember, when we have a constant velocity, that means the net force is equal to 0. So that part's easy. For part C, we start at 3 and we go down to 0. So our change in y is 3. Our change in x is 1, 2, 3. So our acceleration is 1 in the negative direction. So our force is 5 kilograms, our mass, times our acceleration, which gives us a force of 5 newtons in the negative direction. So now it's your turn. Okay, so this one, we know the force. We are looking for the mass. So again, we have our acceleration is equal to the net force divided by the mass. So solving it for mass, its mass is equal to the net force divided by acceleration. Well, we know the net force is 12, so we just need the acceleration in segment A. Well, the rise is 12, the run is 4, so the acceleration is 12 meters per second divided by 4 seconds, and so that's going to be 3 meters per second squared. So I'm going to have 12 newtons divided by 3 meters per second squared. This is positive, this is positive. That is going to give us a mass of 4 kilograms. That's C. Okay, in segment B, this should have been fairly easy because our acceleration is 0, so the net force has to be equal to 0. There is no acceleration, there is no net force. Another thing you might have to do is you might have to find acceleration from a chart. So in this problem, an experiment was carried out to analyze the performance of brakes on a 1,200 kilogram car. We want to know the magnitude of the average braking force on the car. So we want to know our force, and that's our net force, and that's going to be equal to the mass, which we have is 1,200, times the acceleration. So we need to know what our acceleration is. But this time we don't have a graph. We have data. We have an initial speed, v0. We know that, or here we have a distance, delta x. Looking at this, it looks like we are dealing with kinematics because we're looking for acceleration. So we're looking for acceleration. We know initial velocity. We know our displacement. And since we're looking at braking information, that means we probably have a final velocity that was equal to 0. So we're going to have to solve this using kinematics. So remember, we write all of our information. We have our v0, our final velocity, our displacement, and acceleration is what we're looking for. Now with this, each of these sets of data is one complete set. All you have to do is pick one, because if you look at these numbers, they're far enough apart that any minor differences here are probably not going to make much difference. So I'm just going to pick a set of data. I'll pick set 1. So our initial velocity is 10 meters per second squared. Our final velocity is 0. And our braking distance is 7.9 meters. Now time is the one we don't have anything about, any information about. So that means we're going to use this equation. And we are going to solve it for acceleration. And now I'm going to plug in my numbers. So it's 0 minus 10 squared divided by 2 times 7.9. And I could even just round that to 8. It'll probably be close enough. So it's going to be 100 divided by about 16. That's going to give us an acceleration of 6.2 meters per second squared. And then all I have to do is plug that into my equation. So 6.2 times 1,200 is going to give us 7,500, which is right on with this. So that would be our answer. Now it's your turn. You try. Okay, in this one we're doing a similar experiment, but this time we have our initial velocity, but this time we have time. So we still have our mass. We are looking for the braking force again. So we have our initial velocity, our time, we have our final velocity is going to be 0, and we're looking for acceleration. So this time we write down our equation, our variables. And we know that acceleration is what we're looking for. Initial velocity we have, final velocity 0. So this time it's going to be delta x is our unknown. So we need the equation that does not have delta x. So that's our final velocity is equal to initial velocity plus at. And so final minus initial divided by time is going to give us acceleration. So pick a set of data. So we're going to do our 0 minus 10. I'm just going to use the first one again, divided by our 1.2 seconds as acceleration. And so that is an acceleration of about 8.33 meters per second squared. We're going to multiply that times our 2,000 kilograms. So force equals ma. Net force equals ma. So our acceleration times our mass. And that's going to give us about 16,000.